Okay, so this week we'll be talking about correlation and regression. So if we look at our roadmap of where we're going, over here we have our assumptions of independence, heterogeneity of variances, additivity, normality. If they're not violated, we move over to our parametric tests, and if our x and y variables are continuous, we'll end up with a regression analysis or a Pearson correlation to give us information as to how one of these factors depends on the other. I will state that regression is most often used for experimental, when you're designing an experiment, and Pearson correlations are most often talked about when you are doing a correlative experiment where you're taking data from the world and making correlations about those as opposed to running an actual experiment. But they can be, but Pearson correlations can describe experimental data as well. Okay, so both of these things, regression and correlation, Pearson correlation, are analyzing data by fitting straight lines to it. These techniques should be used when you have two continuous variables. You have homogeneity of variances between those two continuous variables. Normality assumptions are met within reason. They are independent. The different samples are independent, as we discussed last week. And we're meeting the additivity assumptions. So I said that I would discuss that this week. We're going to talk about that on the next slide. So we use these tests when we want to know four main things. One is whether two variables covary. Covariance will tell you this, as we'll discuss. The Pearson correlation will tell you this. The M term of a linear regression, the slope term of a linear regression, will tell you this as well. And that's whether two variables covary. You can also learn whether the relationship between the two variables is positive or negative. Covariance will tell you this. Pearson correlation will tell you this. The slope term of a linear regression will also tell you this. You can also learn how much variance in one variable is predicted by the other. And that's pretty important, and we'll talk about. Pearson correlations tell you this, but a better thing that does a better job is the coefficient of determination, R squared. And finally, you can learn, you can figure out how to predict values for one variable based on variable values from the other, and that can be done with linear regression. Okay, so let's start out with our correlative measures. Oh, but first, we have to take a side trip to additivity. So additivity in linear regressions. Factors are additive when the effects of one independent factor on the dependent variable do not change across different levels of another independent factor. So what does this mean? So we have two factors. One is factor A, depicted here on the x-axis. The other is factor B, and we'll say that factor B has two levels. Level 1 is blue, and level 2 is purple. And so in this case, level 1 is up here, level 2 is down here. We can see that the dependent variable depends on how much factor A you have, but it also depends on whether or not you're at level 1 or level 2 of factor B. But as you move across values of factor A in purple, you see the same relationship as you move across factor A for when you're in blue. So as you move across factor A at level 2 of factor B, or if you move across factor A at level 1 of factor B, both of those have the same effect on the dependent variable, which makes them additive. Conversely, if you move across different levels of factor B at level 1, if you move across different levels of factor A at factor B being at level 1, and have a different effect on the dependent variable as moving across different levels of factor A when you're at level 2 of factor B, now factor A has an interactive term with factor B, right? So the level of factor B is affecting how factor A affects the dependent variable. So ultimately, we call that non-additive, and we say that it has an interaction between factor A and factor B. And interactions can be some of the most interesting parts of your experiment. So it's not to say if you see this you're disappointed. You're usually very happy, because interactions between factors are usually quite interesting when they affect a dependent variable. That said, it changes what we can use in our analysis, and in general, when you're dealing with additivity in a linear regression, it's because you're dealing with a multiple linear regression, which we'll touch on at the end here. But essentially, in regression, you need to get around this interactivity, and the way you do it, normally a linear regression is y, which is the dependent variable, plus c, which is slope-intercept, plus slope times x, which is independent variable, slope times x2, other independent variable, plus the error, right? So dependent variable equals slope-intercept plus slope times independent plus slope times independent plus error. Okay, it's a lot to say, but you see what that is. That's a normal equation for a regression, multiple regression. If there was an interaction between the two, one way you could get around it is by adding an interaction term to your equation. In this case, it's d x1 cross to x2. We're not going to deal with this in this class, but that is to say, if you ever do run into non-additive factors, it's not that you can't use regression at all. It's just that you'll have to go put an interaction term in and read about how to do that. Okay, but for now, we're going to assume that our factors are not additive, and we're going to go on to covariance. So covariance is a good stepping stone to get you to Pearson correlation, which is a good stepping stone to get you to coefficient of determination. Covariance tells you three things. It can classify data into three types. Relationships that have a positive trend, which is shown here, relationships that have a negative trend, and relationships that have no trend. And so positive trend means that as x increases, or as as the x variable increases, the y variable also increases. Negative means that as the x variable increases, the y variable decreases. And no relationship means that there's no prediction as to what's going to happen in y as x increases. And so the equation for covariance is the measurement xi minus the mean of x multiplied by the measurement yi minus the mean of y. So that's your x and your y of particular points, subtracted by the means of each one, summed together, divided by n minus 1. Right? It's very similar to the equation for sample variance, but now we're doing sample covariance. And if we draw the mean of x and the mean of y onto one of these axes, you can see why the negative and positive relationships exist, right? So in this particular graph where I've drawn the means, you're going to get a negative number for your covariance, which means there's a negative relationship between the two variables. And that's because if, in these upper terms, right, if your xi measurement and your yi measurement are both above their means, it's going to be a positive multiplied by a positive, which will give you a positive value for your covariance. If you're down here, you'll have a negative value and a negative value. That'll also give you a positive for your calculation of covariance. But if you're over here or here, now you're going to have a negative multiplied by a positive, which will give you a negative value for your covariance. And therefore, if most of your points fall in this quadrant or this quadrant, you're going to have a negative covariance. If most of your points fall in this quadrant or this quadrant, you're going to have a positive covariance. So in R, the function we use for covariance is COV, open paren, x data, comma, y data, close paren. And these x data and y data are arrays. Okay, so what are the problems with covariance? The big problem with covariance is that covariance is sensitive to changes in scale. this means that the absolute number that we get for covariance is not really useful for much of anything. So if I have two data sets here, or three data sets here, I have my red circles, my green triangles, and my blue squares. My red circles have a covariance of 4.6. And then you could see that my green triangles have the exact same relationship as the red circles, except I multiplied the values of each one by 2, right? So it's just doubled in scale. But the covariance of the triangles, despite having the exact same relationship between the x and the y as the red circles, right? They're all still on the same line. Their covariances are very different, right? 18.6 is much larger than 4.6. This doesn't say anything about how much better they are at being a line. It just means that it's just because covariance is dependent on the scale, right? These numbers are larger, and therefore you have a larger covariance. Whereas for the blue, it has a different slope, but essentially it covers it covers somewhere in between what the green and the red covers in terms of its scales, and therefore it has a value of covariance in between the green and the red. So all of these numbers are meaningless other than the fact that they're positive, right? And so the fact that they're positive says, okay, covariance tells us there's a positive relationship between whatever this x is and whatever this y is for these three data sets. But it doesn't tell you anything in your absolute value. So that's where Pearson correlation comes in. Pearson correlation takes the scale into account. So if this is your covariance, your Pearson correlation is going to say, all right, I'm going to take that covariance and divide it by the square root of the two variances multiplied together, the variance of x and the variance of y. And what this is essentially doing is scaling the covariance for the variances in x and y, which makes the Pearson correlation r, which it should be little r here, but it could be little or big. You can use them interchangeably. Little r ranges from -1 to 1, with values closer to 1 indicating more variance in the dependent variable being explained by the independent variable, right? So if we go back to our data set here, our covariances were as such, but our Pearson correlations for all of these are going to be 1. And that's because all three of these are a line, which means that all of the variance in one variable is explained by the other, right? All of the variance in y is explained by the variance in x. So if you say I go over 1 unit in x, I see a 1 unit increase in y. If I go over, for the green triangles, if I go over 1 unit in x, I see 1 in y. For the blue squares, if I go over 1 unit in x, I see a 2 unit, or sorry, yeah, if I go over 1 unit in x, I see a 2 unit increase in y, right? So yeah, your dependent variable is entirely predicted by your independent variable when r equals 1. So to measure Pearson correlation in R, you use this core.test with your x data, your y data, and then put method equals Pearson for the Pearson correlation. And so to get a better feel for exactly what Pearson correlation is telling you, here's some examples of what Pearson correlations would be in different scenarios. So again, if we have a positive sloped line, right, we have a 1. If we have a negative line, we have a -1. It doesn't matter what the slope of that line is. Any positively sloped line will have an r of 1. Any negatively sloped perfect line will have an r of -1. And a perfectly flat line will have an r of 0. But if you start to become less and less of a line and more just a cluster of points, now your Pearson correlation will get closer and closer to 0, right? And that will come from the other angle as well if you have negative correlation. And then this bottom row illustrates where Pearson correlations are very poor to use. All of these at the bottom would show a Pearson correlation of 0. But as you are probably aware from your eye, you can see that these things do in fact have correlative relationships with each other. But those relationships just happen to not be a line, right? This first one is some sort of sinusoidal wave function would probably fit this relatively well, right? And that means that x is correlating with y in a sinusoidal function, but the Pearson correlation is entirely based on drawing a line through the data, and therefore there is no linear correlation between these two things. So this is where Pearson correlation is bad. So you really only want to be using Pearson correlation when you are sure that it is a linear relationship that you're trying to query between your dependent and independent variable. Okay, so Pearson correlations also come with p-values. The p-values increase when the amount of data increases, which increases your confidence. High p-values mean that the probability the Pearson correlation was achieved by random chance is less. Right, so if we go back to our data, we have our covariances, we have our Pearson correlations of 1, and in this case, all three of these would have a p-value of 2.2 times 10 to the negative 16. That's because in all of these cases, the R is 1, and the number of points is 7. And so if the R is 1 and the number of points is 7, then you have a very small likelihood that this particular distribution of points was generated by chance, right? But in another case, now we have an R of 0.93 for the red and an R of 0.6 for the blue. The 0.93 means that it's obviously more of the Y is more of the Y variable is being predicted by the X variable. More of the dependent variable is predicted by changes in the independent variable than is for the blue, which is only a 0.6, which you can see is hugging a line less, or the Y is less well predicted by the X. There's 7 points in both of these data sets, but you can see the p-value is much less in the data set that hugs the line more closely, and that's because it is less likely that you generate perfectly linear data than it is that you generate dispersed data, right? If you were to just put random points onto a line, the thing that you would get is R equals 0, right? It would be not correlated with each other, and that would be random chance, and p would be 1, right? But for a given 7 points, right, the least likely thing that those 7 points can do is generate a line. And so if your R is 0.93 and you've got an R of 0.93 with 7 points, that p-value is going to be less than if you have 7 points with an R of 0.6, which is much closer to what you would expect, R of 0 being what you would expect. And so that's a p-value is not as low as things that are closer to a line. So the p-value is dependent not just on the number of points, it's also dependent on how close the data is to a line. Those two things together tell you how likely it was for these points to have just randomly become like this on their own, right? Okay, so that's all I'll say about p-value for now. The problem with Pearson correlation. So Pearson correlation is doing a pretty good job now of telling us how close things are to being a line, how close we are to saying that all of y is being predicted by x. But if I tell you that a Pearson correlation of 0.9 is twice as good at making predictions as a Pearson correlation with an R of 0.63, that's really not all that intuitive, right? 0.63 times 2 is 1.2, right? So 0.9 doesn't feel like it's twice as big as 0.63. So it's really not intuitive that is that way. Ultimately, we want an easier to interpret value for just how much variance in one variable is explained by variance in the other. And so R is better than covariance, but it's still not perfectly intuitive, and that's where R squared comes in. So R squared is the coefficient of determination, and R squared is exactly what we want. It is the proportion of the variance in the dependent variable that is predictable from the independent variable. And R squared, as you might have imagined, can be calculated by squaring R. R squared can also be calculated using the sum of squared residuals, which we'll go over in a second. And that has the advantage of being able to provide a fit for any shape, not just a line. But in this case, let's talk about it in relation to the Pearson correlation. So here's our data that we've been dealing with. We have a covariance, we have our R's, which are Pearson correlations, p-values, right? So now, if I show you the R squared for the red circles and the R squared for the blue triangles, now you can say something like, for the red circles, 87% of the variability that we see in Y is explained by X. And for the blue triangles, 36% of the variability that we see in Y is explained by the variability we see in X. So we can really make a concrete statement about how much variability in Y is accounted for by X, how much variability in the dependent variable is accounted by the independent variable. We can also say things like, well, 0.87 is about 2.4 times as large as 0.36, and therefore the data in the red circles is 2.4 times more variation in Y is explained by X for the red circles than as for the blue triangles. All right, let's move on to linear regression. So linear regression is all about fitting a line to data such that a slope m and a slope intercept b minimize the sum of squared residuals. So we'll talk about what that means in a second. The equation would be the dependent variable equals the slope m times x, which is the independent variable, plus b, which is the slope intercept. So if we have our data here, we can fit a line to that data using the LM function in R. So LM, open paren, x is a function of your x data, y is a function of your y data, and that'll give you a model. And the way that this line in R gets fit is by minimizing the sum of the squared residuals. I'm showing you in green here all of the residuals. The residuals are the distance from the fitted line to the points. And if you square those, you have the squared residuals. And so if we go back to our coefficient of determination, we could calculate it using the Pearson correlation, but the alternative formula for it is 1 minus the sum of squared residuals of the fit, which I'm showing here. These are the residuals. If you square them, you have the sum of squared residuals, minus the sum of squared residuals of the mean. And so x bar of y is shown here going across, and then coming out from x bar of y, we have the residuals of all of the data away from the mean, right? So SSR away from the mean is summing all of those and squaring them. And so if you take 1 minus the residuals of the fit divided by the squared residuals of the mean, then you end up with your R squared value. It's another way to calculate R squared. To calculate the sum of squared residuals in R, you use the fitted function, fitted with your model name, which you've gotten out of your modeling function. Fitted gives you the values of y as predicted by the line that's been fit in the linear model. And so if you wanted to calculate your sum of squared residuals, you take your y data, you subtract it from fitted model data, and then square that. And you get your sum of squared residuals for the fit. If you wanted your sum of squared residuals for the mean, you would simply take your data subtracted from your mean squared, which you'll recognize is pretty close to the variance, except you don't divide by n minus 1. So that's your sum of squared residuals and an alternative way of calculating your coefficient of determination. And the residuals are also the way that R calculates its regression line. You can also calculate regression lines by hand, but we won't cover that here. And I really don't think anyone does that anymore unless they're doing it for math class. There are plenty of great things like R that will calculate this for you. Okay, so in R, more about this linear model function. X depends on X data, Y depends on Y data. You can use a summary and then the model name in order to get a summary of your different variables here. So what you should focus on here is M and B. M and B are your slope and your slope intercept for the line that is predicted from your linear model. The other thing you have here is your a description of the residuals. It's not the squared residuals, it's the median of the residuals, but it gives you an idea as to how far your points are away from your line. And so together, these things describe the line that the R is outputting. And so why are they so useful? Well, once you have your slope and slope intercept, you can use your slope and slope intercept to predict values of your dependent variable from your independent variable. So you can say, all right, if my independent variable is 8.5, now I can make a prediction as to what my dependent variable will be based on this line that I have fit. And how good of a prediction that will be is described by R squared and the p-value, which is the confidence in how good your R squared value is, right? So higher R squared will mean that the predictions that your linear regression makes will be more accurate than for R squareds that are lower. That will say that the predictions made by your linear regression will do a less good job at predicting your dependent variable. Okay, and finally, multiple regressions. You can do this not just for a single independent variable. You can say m1 plus x1, m2 plus x2, m3 plus x3, as many as you want. It works very similarly to how you would do things in a linear regression. You just add more and more variables. There are some special rules. One in particular you want to know is that you want to make sure that your independent variables don't correlate too heavily with each other, don't depend too heavily on each other, or else it makes this very meaningless in terms of the things that it outputs. That I think is the main consideration that you want to keep in mind. You just don't want the independent variables to correlate too much with each other. Outside of that, there's a whole bunch of really great how-tos on multiple regressions. We're not going to cover them in this course, but if you ever need to do them for your research, I'm posting a YouTube link to StatQuest where they cover multiple regression. He does a really nice job in that video if you have interest in learning about how to do a multiple regression. But for this, you just know that it's possible and the information's out there if you want it. But for the actual exams and content of this course, we'll focus on just single linear regressions. So this should be everything you need to complete your workshop on Wednesday. Hopefully this was not too long-winded and was informative for you.